on, everything is fine.
Yeah, so like mentioned, I'm Justas Barauskas, and topic of my presentation is manufacturing of lightweight concrete using green technology by curing in carbon dioxide environment. So, content of this presentation, I will introduce what problem we face, what is foam concrete, what is carbon dioxide curing, and present my research with conclusions. So first of all, introduction. In 2020, the construction sector generated as much as 38% of global carbon dioxide emissions. The amount of CO2 emitted during cement production alone was about 0% of global emissions. So, trying to slow down climate change, International Energy Agency set to achieve carbon neutrality in construction sector and cement production by 2050. To achieve such goals, we need to use new green technologies like carbon capture, accelerated carbonation of concrete. So, my topic, I'm making lightweight concrete, so foam concrete. Foam concrete is one of the lightweight concrete types. It's made by adding foam agent into mixed mortar that allows the mixture to maintain air voids. The foam concrete has the properties of porousness, lightweight, heat insulation, and sound absorption. So let's talk about carbon dioxide curing. So there are three main methods how we can make accelerated carbon curing of concrete. So first of all, most simple, where samples are placed in carbonation chamber containing environmental pressure but concentrated carbon dioxide gas. Another method could be pressurized. In this method, both the carbon dioxide pressure and the concentration are higher than the natural curing carbonization. It's mostly used for research because it is the most effective. And third method could be flow through. The gas is constantly flowing and exit at the opposite end of the chamber, then the inflow. This method can be used to control the temperature, humidity, carbon dioxide gas concentration, and flow rate. So chemical reactions of carbon dioxide curing. So when concrete is exposed to CO2 in a natural environment or in a concentrated environment, gas penetrates through surface defects, pores, or cracks. The carbon dioxide reacts with cement hydration products. So the hydration should start first, and then carbon reacts with calcium hydroxide, which forms calcium carbonate, and also carbon dioxide reacts with clinker minerals and forms calcium hydrosilicates and calcium carbonate as well. So the purpose of my study was to determine what effects have different carbon dioxide curing time on carbonation depth of lightweight foam concrete. So composition of the concrete, I have made few different compositions and chosen this one in the slides because of its density and other workability properties. In this composition, water glass was used to speed up the setting of concrete so that the concrete does not collapse and retains its shape during hardening. After samples were hardened enough to take them out of the forms, they are put in the carbonation chamber. During this process, the carbonation chamber is maintained at 20 degrees Celsius, 65% of relative humidity, and concentration of carbon dioxide at 20%. So results. So these images are when samples were taken out straight of curing chamber, and they were split and spread with phenolphthalein, which shows how much of the cross section is carbonated. So the purple area is non-carbonated, and the clear area, which you can just see concrete, is carbonated. So When the samples were in the curing chamber for 5 hours, the carbonation depth was 12 millimeters, and the sample which was left in the air for 5 hours, the carbonation was 0. And after 1 day, the carbonation depth was 15 millimeters, but the carbonation degree was bigger. We can see that from the that there are no solid purple color on that sample, but we cannot assess carbonation degree by this just using phenolphthalein. And after 3 days, the carbonation depth was 21 millimeters, and in the air, it showed that it started to carbonate, and it was 1.5 millimeters. Also, some of the samples were used by mixed curing, so they were cooled for example, 1 day in the carbonation chamber, and then 27 more days left in the air. So after combined of 20 days of curing, we have split those samples, and the result we got is that after 5 hours in CO2, the carbonation depth was almost 28 millimeters. After 1 day, it's similar, but once again, carbonation degree is higher. And after 3 days, it's already fully carbonated. So conclusions of this study. So we can see that CO2 curing is effective for foam concrete. After only 5 hours combination chamber, 43% of sample cross-section area was carbonated. Carbonation reaction does not stop when removed from carbonation chamber after combined carbon dioxide and air cooling of 28 days. In all cases, carbonation was bigger, and carbonation reaction when cooling only in the air is slow. After 28 days of cooling, average carbonation depth was only 10 millimeters, which is less than what we got when cooled 5 hours in carbon dioxide. So that was it for me. If you have any questions, please ask. I will be happy to answer them.
So thank you, Justas. Was an interesting research. I would have a question for you. So in the introduction, you were speaking about the significance of the construction industry regarding the CO2 emissions, and where later you demonstrate how the curing of the concrete could reduce the emissions. So what do you think are the main barriers for implementing this method widespread in the industry?
I think for now, it may be difficult to get the amount of carbon dioxide we need for this. Also, I think it could now only work for the small units, for example, masonry units or other samples that are made in the factories. So we can't carbonate poured on-site poured concrete, just that it made in the factory.